Let's start with the second lecture by Chris Beem, who is going to tell us about vertex separate algebras today.
Okay, so thanks for coming back. There's going to be a bit of discontinuity between the lectures by design, but nevertheless, I apologize. Last time, at the end, I think I had basically managed to recount the extraction of some sort of meromorphic operator product algebra, starting out with 4-dimensional n equals 2 SCFTs in general. It was just based on representation theory and CFT generalities. We inevitably have some intuition for these sorts of algebraic objects because we run into them early in our life when we're studying 2-dimensional conformal field theory as chiral symmetry algebras, or chiral algebras as they're often called in the physics literature, although this is confusing because the mathematicians have defined a different thing called chiral algebras. In some slightly weaker setting, if you have 3-dimensional topological quantum field theories, then hopefully many people are familiar with the fact that if you have boundary conditions that retain a dependence on the complex structure, then you get some sort of meromorphic operator algebras on the boundaries. So there's some intuition for these things, but there's also quite a bit of rigorous mathematical formalism about them. And in that setting, they go under the name of vertex algebras or vertex operator algebras. And so that's what I'm going to talk about today. This is a sort of a big subject, and it's an especially sort of annoying, thorny subject when you open the textbooks. They're full of equations that you really don't want to look at. So I'm going to try to give some sort of streamlined trajectory through the basic theory today that will make it so if anyone at some point wanted to open one of the standard textbooks, there's one by Victor Katz, there's one by Ed Frankel and David Ben-Zvi, then you would be more equipped to do so. So, yeah.
Sorry, before starting, is it possible to explain in physics terms what the mathematicians call a chiral algebra?
Not really. I mean, it's close to this, but it's a gadget that lives in the world of algebraic geometry, and so it's when you try to generalize the world of when you try to generalize something like this story to a setting where you are thinking about working on general Riemann surfaces, but not Riemann surfaces, thinking of them as algebraic curves. And you want sort of everything to make sense in the language of algebraic geometry, where you talk about sheaves and schemes and things instead of local coordinates and expansions and powers of things. It was defined. They were defined by Beilinson and Drinfeld in some famous work. But that even more so than what you get when you open the vertex algebra textbooks. It's at least in the first instance unrecognizable to a physicist, although you can eventually see that there's supposed to be some link.
Thanks.
Okay. So here's the plan, more or less. I will define vertex algebras and vertex operator algebras. That's going to take longer than you think. I will recount what I think are sort of some important structural results that follow from the definition. None of them are surprising if you have a physics intuition, but it's nevertheless important that they follow from the definition if you want to be rigorous. I will gesture towards a way that we tend to approach these things in practice in terms of something that I would call the vertex algebra or VOA bootstrap. And then I'll finish off by discussing a little bit from the mathematical perspective, how people tend to think about sort of niceness conditions on vertex algebra. So if you're running into these things in the wild, what sorts of characterizations might you want them to have? What sort of classes of algebraic objects might you hope that they fall into? And that's going to be relevant for the lecture next week when we come back and sort of return to the things coming from four-dimensional SCFTs. Okay. So with apologies to people who aren't looking for idiosyncratic definitions, here we go. I'm going to have a lot of definitions in this talk. So we define a field on a vector space. Don't think that it's immediately going to be too close to something you know. A field on a vector space is an element of endomorphisms of the vector space. So those are linear maps from the vector space to itself, adjoin formal power series in Z. So that's something that you can write this way as an infinite formal series Z with all positive and negative powers where the coefficients are some linear map from your vector space to itself.
Is this supposed to be a finite dimensional vector space?
No, not necessarily. And in practice, to get interesting examples, once we add all the rest of the definitions, it's going to be always infinite dimensional.
So what's an endomorphism on an infinite dimensional vector space? Is it a linear operator? Is it a bounded linear operator?
It's a linear operator. That's it.
But is it defined on the whole vector space? Is this important?
I don't think this is going to be important. Of course, this is an issue one should ask.
I'm asking because that's the question where I stumbled while reading some of these vertex operator algebra papers, and I didn't see it anywhere explained.
Well, there's certainly no boundedness condition because I haven't. It's a bare vector space at the moment.
Okay, there's no topology anyway.
There is no topology.
Okay.
Sorry. It's okay. There's probably a good question and answer to have in the genuinely most general case. I should say that fairly soon we're going to restrict to situations where your vector space is a direct sum of finite dimensional vector spaces.
Okay.
And in that case, having it mapped to itself, I think, is well defined. It's not bounded, but there's some implicit topology in which it will be defined. And there's a condition. It's not a completely general one of these formal objects, but you demand that given an arbitrary element of your vector space, you are bounded in the negative powers of Z that act non-trivially. So you're going to demand that these components of the series annihilate any given vector for a fixed vector if you take J big enough. So that means that if you go to high enough negative powers of Z in this expansion. So that means that the thing that you get when you act on a vector with this object is going to be an element of your vector space adjoin formal Laurent series in Z, which is what these double curly or double curved brackets mean. It means that you have a formal infinite series in Z. It's bounded in powers below, but not above.
Actually, should there be in J sufficiently large negative or something like that? Because
that's right. Sorry, I'm sorry. In a moment. That's absolutely right. Yeah.
Okay.
So just as a small remark to observe some spiritual kinship with the careful analysis from Slava's talks, you can think of elements of these formal series in Z and Z inverse as formal distributions whose test functions are Laurent polynomials in Z. So if you're given a Laurent polynomial in Z, so that's bounded below and above in powers of Z, then you can define a pairing between these infinite things and the finite things that's called the residue pairing, where you multiply them together. Multiplication is well defined between a Laurent polynomial and one of these formal things, even though multiplication between the formal things is not well defined because you're going to have some sort of infinities. So you take the multiplication and then you take the -1 piece. So you take the piece that has z to the -1. So it looks like a formal version of doing a residue integral. And so in that sense, the things that were called fields in this definition are operator valued formal distributions on your vector space. So then the key definition, which always looks terrible to me, and I'll give a slightly nicer version that applies in a special case momentarily, is that if you have two fields on a given vector space, they're called mutually local if the following condition holds. You pick arbitrary elements of your vector space and you pick arbitrary elements of the dual space being linear functionals on your vector space. And you ask for the pairing between your dual vector and A and B acting in sequence on your first vector at different formal coordinates. So the thing that you get when you act this way is going to be something where you've got powers of Z and powers of W around. There's some boundedness conditions because of the field definition that if you sort of sufficiently negative powers are supposed to vanish. And so in practice, what you get is something that lives in this funny space. C double bracket Z double bracket W. So these are formal Laurent series in W whose coefficients are formal Laurent series in Z. This thing has a global bound on the negative powers of W. And then for a fixed power of W, there's a bound on the negative powers of Z. But in the full expansion, you could have arbitrarily negative powers of Z. If you do things in the other order, you act with A then B, then you get something that lives in the space with the role of Z and W reversed. So these are different spaces. And the claim is that the definition is that you'll call these fields mutually local if these two elements of these two spaces are actually expansions of a single element of this funny space, which is a series where you have finitely many powers of Z inverse, W inverse, and Z minus W inverse, and then you have arbitrarily positive powers of Z and W. So just to see an example of how this works, if you look at the expression 1 over Z minus W, that thing, if you think of W being smaller than Z, or if you just do sort of formal manipulations, you can expand in this space CZW like so. So this thing has globally bounded negative powers of W. In fact, it has no negative powers of W. And then at a fixed power of W, you have a bounded negative power of Z. And if you expand the way that you would if Z was less than W, you get a different thing that lives in this other space where the roles of Z and W are swapped. And so these are two elements of these two different spaces, which are expansions of the same element of rational functions of Z and W. Of course, you have some, you probably have some impulse to treat this more analytically, because of course, what I'm really doing here is doing the expansions that are relevant for these orderings of the magnitudes of Z and W. In the most general definition of vertex algebras, you don't get to make things analytic. Everything is formally algebraic. But in a moment, let's see, in a moment, not next, but in a moment, I will introduce a condition under which things become a little bit more analytic, and you don't need to talk about these formal series quite so much. Okay, so we haven't defined a vertex algebra yet. A vertex algebra is defined in terms of this notion of fields and locality, and it's a quadruple. It's a vector space. It's an element of the vector space, which is the vacuum. It's an operator on that vector space, which is unfortunately named T, not to be confused with the Virus stress tensor that you will see later in this talk and that you know well. So it has an element T, which is the translation operator. You should think of it as like partial differentiation. And it has an operator or a state operator map, which is called Y, which sends an arbitrary element of your vector space to, I didn't write it correctly. Sends an arbitrary element of your vector space to a field in this usual endomorphism space that I was talking about before. So the field condition, again, being this truncation in negative powers. And there's a slightly different convention for moding than what I wrote before for a general field. When you write out the Z expansion of an element of this of the fields that you get from this state operator map, you write it this way. So AN comes along with Z to the minus N minus 1, and that's built so that AN is the thing that you get by doing sort of a formal residue integral with a power of Z to the N. And there are three axioms or three sets of axioms associated to this. The vacuum axiom says that the operator associated to the vacuum state is just the identity operator. And that if you have an arbitrary state and you take the operator associated to it, the field associated to it, and act on the vacuum, first of all, you don't get any singularities. You don't get any negative powers of Z. So you have double square bracket Z. This means formal series in Z with no Z inverses. And if you then take the limit where Z goes to 0 of the field associated to A acting on the vacuum, you get back the state A. So this is hopefully intuitive that this is what you would define if you were trying to introduce some sort of idiosyncratic definition of how the OPE works in some very weak setting where we don't have a lot of extra structure. There's a translation axiom which says that the vertex operator or the field associated to this translation endomorphism T acting on a given state is just given by the partial derivative in the formal sense. So if you have one of these fields, it's an expansion in Z in formal series, you can take a formal partial derivative. And the translation should act trivially on the vacuum state. And then the third axiom is locality, which says that for any two states, the associated local operators or the associated fields are supposed to be mutually local. And this turns out to be the condition that does all the work. Okay, so this is a very general definition. It, in principle, allows for examples that have very little structure. So I haven't talked about sort of energies of states or any sort of grading like we would normally have in a conformal field theory where states and operators are labeled by conformal dimensions. We're not assuming that the vector space of states has a norm or an inner product or a Hilbert or has some Hilbert space structure. And so there's no sort of convergence conditions that we can ask for the various formal series that we're getting in Z. Nevertheless, this is a perfectly good definition, modulo my not being totally sure about the answer to Slava's initial question. Slava, I think the answer to your initial question was actually they are bounded.
Who bounded?
Well, they're globally defined.
They're globally defined. Yeah, that's for sure. I have a question about the last point about no correlation functions, because I'm thinking that suppose that you want to define a correlation function of two y's, like the ones that are like, suppose I want to define a 2-point function of two y's.
Yeah.
Then if I use this locality axiom, which was the last axiom, then I could say that by the locality axiom, there is some power series of which these two guys are expanded.
Yeah.
And so I could call that power series, which involves some powers of 1 over z minus w. I could call this a 2-point function of two y's, but I would not probably be able to generalize it to hyperplan functions. So
well, even that. So you could call that a correlation function, but it isn't a function yet, right?
It isn't a function. It's some power series, yeah. And moreover, I would not be able to do something like that for higher.
No, you're going to be. You can compose more. You can compose more of these fields. But when I said no correlation functions, I meant if you really wanted it to be locally a function and not just something that lives in a appropriate world of formal series.
Okay.
If you start taking higher point functions, you're going to have more things living in more of these spaces with, well,
yeah,
it's going to be formal.
It's like an operator values kind of series, right? You can
not if you put in sort of the appropriate element of the dual space. I mean, you can build things where you don't have.
What is the appropriate element of the dual space?
I mean, I was thinking of sort of going back to something like these sorts of expressions. So you might choose phi to be the vacuum state and phi tilde to be something that just measures like the coefficient of the vacuum.
Okay. I see. Okay.
Is there such a phi tilde? Yeah.
But the issue is I think not without saying more about the vector space.
Okay.
Yeah, exactly. You need an inner product there.
Well, you don't necessarily need an inner product, but I mean,
to have a map from phi to phi tilde.
Correct. Correct. Okay. Good. So, in a way, I've been giving this definition as sort of an apology for how formal the definitions look in the textbooks. In practice, even in fairly general situations that we encounter in physics with these things, one usually has at least a little bit more structure. And one thing that we tend to run into is some sort of grading structure on our vector spaces. This is certainly the case in the things that I'm going to be talking about in 40 again next week. So a Z-graded vertex algebra has more to it. A Z-graded vertex algebra is one for which your vector space is Z-graded. It's occasionally given as a sort of even weaker definition. It's a genuinely Z-graded. I'm going to take Z-graded with grading bounded below. So my vector spaces decomposes into a direct sum of vector spaces labeled by integers bigger than some number k that I don't know, but it's some fixed number. The translation operator increases grading by 1. And then the fields associated to homogeneous elements of my space of states. So if A is an element of the H graded part of my vector space, then when I give it expansion in terms of these endomorphisms, those things are going to act between definite weight spaces. So A sub j is going to act between the weight n part and the weight n plus h minus j minus 1 part. The fact that you have this funny shift is a relic of using the mode conventions that are standard in the math literature that I gave before. It makes sense in this graded setting to redefine the moding. And now I'm going to say that the same field associated to an element A has this expansion, where instead of having minus n minus 1 in this exponent, I have minus n minus h. And that's the thing that you run into in physics textbooks, where h is the conformal dimension of the associated operator. So the difference is whether the subscripts have parentheses around them or not. And for these non-parenthetical moded endomorphisms, they act by decreasing the grade by j, where j is the subscript. And in this Z-graded setting, it turns out that the conditions for locality can be rephrased a little bit more analytically. And this is because if you restrict to definite graded subspaces, you sort of only get so many powers of Z involved, because the place that you get sort of too many powers of Z is when you can, well, in the graded setting, you would be going to higher and higher or lower and lower grade in the vector space. So here's a statement. You have to prove it. It's proven in the textbook by Frankel and Benz-V. If you have Z-graded fields, then they're mutually local if the following set of sentences holds true. So for Z bigger than W in absolute value, so now Z and W are numbers, then this composition A of Z, B of W actually exists as an operator on your vector space and can be analytically continued to a meromorphic valued or a operator valued meromorphic function of the two coordinates Z and W, where the singularities are only at Z equals 0, W equals 0, and Z equals W. So the places where you would expect from sort of a physics picture. And moreover, the order of the pole at Z equals W is uniformly bounded. So acting on a given element in your space of states, you only get so many negative powers of Z minus W. For W bigger than Z, the same should hold for the opposite ordering. And then the things that you define by these analytic continuations should be the same meromorphic, the same operator valued meromorphic function. So this is now getting closer to what one's intuition is, I think, normally coming out of physics, that you're supposed to be able to make sense of pictures where you literally have operators living at points, and they make sense where the coordinates of those points are actual numbers, and you have sort of finite poles when things run into each other. But that follows based on this still rather thin definition of a vertex algebra. We still haven't had to induce Hilbert spaces or anything. And then an important fact, which you have to prove, it isn't totally obvious, is that the locality condition implies an associativity condition, which is that if you write a composition in this different way, so what am I doing here? I'm taking the field associated to A with sort of displacement value Z minus W acting on B, and then taking that and displacing it by W. Then that should give me an operator valued meromorphic function that analytically continues again to the same thing. So the picture here, of course, is just the usual associativity of OPE. It's saying that if I have A of Z, B of W, and here's my origin over here, then I can think of doing an OPE associated to this sort of collision, taking what I get and then thinking of that as an operator that acts sort of at the origin. And that follows, again, from the axioms, namely the locality axiom. And if you appropriately interpret this equation that I've written, you then have an equation that looks like an OPE. So appropriately interpreted, meaning that the left-hand side is an element in some funny space that you need to analytically continue, and the right-hand side is an element in this other funny space that you analytically continue, and they analytically continue to the same thing. Okay, so we get an OPE, and we can even treat it as a relatively analytic sort of statement.
So the reason why we managed to prove it with so few input is because we are limiting to integer powers of z, I guess. Otherwise, it would be...
Yeah, absolutely. So there's a lot of structure here. I mean, everything, in a sense, things work because because you're doing algebra, basically, and you're working with these formal series that are reasonable algebraic objects. I think you would struggle in a case where you didn't have this sort of simple integer space structure. Okay. So those are axioms. That's great. We should, or I should say a little bit about the process of checking or confirming that those axioms hold. So in practice, it looks like the locality axiom is going to be hard to check if you're just working axiomatically. It's a statement which is supposed to hold between all pairs of these vertex operators associated to states. So it looks like a lot of conditions, like we know in the conformal bootstrap, solving the associativity conditions of the OPE in principle seems like it's an infinitely big problem because you have to choose all possible correlators. But the nice thing in this very simplified vertex algebra setting is that you can often reduce the check to a finite number of conditions. And this is achieved through the normally ordered product. So if you have two fields, you can define a normal ordering of them. This is similar to the normal ordering that you have of free fields in conventional quantum field theory, except that we don't assume that these are free fields, and so their OPE could be sort of complicated. Nevertheless, you define this thing where you, if you look at what's going on, you're taking the modes of the A operator. So A appears first here. You're taking the modes of the A operator that come with singularities in Z and moving them to the right, and you're taking the modes that don't have singularities in Z and you're putting them on the left. So this is sort of similar to what you're doing in conventional free field theory, except that now, in principle, you don't really know what's going on with the modes of B. And so in particular, for example, this is not a commutative construction. So this treats A and B on different footing. But nevertheless, if you do it like with the usual normally ordered product in QFT, this gives you something which is well defined in the limit when the two operators come together. And that defines, oh, sorry. I don't know if you can see, this is a W. And that defines a local field in the limit where Z approaches W of this normally ordered product. And that thing is also called the normally ordered product of A and B, but now it's denoted with these parentheses. And it's well defined, and it's not hard to check that it is necessarily, following from the axioms, the field that you associate with the state that comes from acting with A-1 and B-1 in sequence on the vacuum. It's also, and this full normally ordered product is what you get in the OPE left over after you remove all of the singular terms. This should have been from n equals 0. So even in an interacting vertex algebra, in the sense of having complicated OPEs, you have a sort of canonical, well-defined notion of composition of operators at the same point. The algebra that defines on your set of operators or on your vector space V is complicated. It's not commutative and it's not associative. So you can check in principle if you look at how this expansion works, and even in the threefold case, you can check that you're not going to have a commutative normally ordered product unless you have a commutator of modes, which is 0 between a-1 and b-1. And in general, unless a much more complicated condition is satisfied, you're not going to have an associativity condition of this composition. Okay, so you have a nice operation to compose local operators, but it doesn't give you a particularly nice algebraic structure on your vector space. Nevertheless, there's an important result. It's known as Dong's lemma, which follows from locality, which is that if you have 3 mutually local fields on a vector space, then when you take the normally ordered product of 2 of them defined in this way, that will be mutually local with the third. And so because you can iterate this procedure, this means that mutual locality for one or a few fields will immediately imply the existence of a large number of local fields. And so you can get a lot of the locality axiom satisfied with only a little bit of input. Okay, so let's finally talk about an example that everybody knows super well, so it's slightly less abstract. And of course, this is a case that you know so well that you don't need anything new proven about it. But nevertheless, let's see how sort of this axiomatic framework comes into play in this setting. So we're going to talk about the Virasoro algebra. The starting point is the Virasoro Lie algebra, of course, which is this infinite dimensional Lie algebra spanned by LMs, where M is in Z, and a central element named C. Hopefully this is all of your favorite infinite dimensional Lie algebra. And then you build a space of states to start with. The fancy way to describe the space of states is that you take the induced representation of this Virasoro algebra, starting out with the one-dimensional representation on which starting out with the one-dimensional representation of the subalgebra consisting of LMs where M is greater than or equal to -1, along with the central element, on which all of those LMs where M is greater than or equal to -1 act as 0, and the central element acts as a arbitrary complex number C. But in less fancy terms, this is the vector space that you get by taking the span of elements acting on a vacuum vector of L-2s, L-3s, L-4s. And of course, these don't commute, but there's a so-called Poincare-Birkhoff-Witt basis. So you can choose a non-redundant basis according to some ordering where you go L-2s first, then L-3s, L-4s, and so on. So given that vector space, you start out with this state L-2 acting on 0. That's a vector that you name omega if you follow the math conventions. And you define a field associated to it. So the map Y on it is equal to this standard thing that you know from 2D CFT or string theory. It's this linear combination of the LMs with Zs. And a direct calculation then shows that that stress tensor is self-local, and it's self-local, and its OPE, the singular terms in the OPE, are exactly the ones that we are used to from the Virasoro, or from the OPE of the holomorphic stress tensor in 2D CFT. And then you're done, because having that state operator map for omega, and then using the fact that you can get all of these other states, the state operator map for all of these other states is implied by my rule for normal ordering and for taking derivatives. That gives you a state operator map for all of your states. And by Dong's lemma, they're all going to be mutually local. So even though there's a bunch of machinery involved, and even though I didn't prove something you didn't already know, nevertheless, this is a nice demonstration that you can get a vertex algebra, you can show you have a vertex algebra without doing an infinite amount of work in terms of verifying this locality property in this abstract setting where I don't need to rely on some sort of underlying assumptions about having an honest two-dimensional quantum field theory with Hilbert space, blah, blah, blah. Okay.
Just to see how obvious it is that that you have a state operator not for all of V. Is it obvious to see that L-1 is a translation operator? For a mathematician, for a physicist, yes.
Okay, good. So I have like the right answer and then an annoying answer to that question. I haven't thought about how easy it is to stare at this and immediately conclude that L-1 will act as the translation operator with respect to all of the local fields that you define this way. Although I think that you probably would be able to show it without doing an infinite amount of work. Strictly speaking, the annoying answer, which is the wrong answer, is that it turns out that you don't actually need the axiom about the translation operator in order for things to work. Even though it's usually phrased as a separate axiom, you can actually, given something that satisfies all of the axioms except the translation axiom, you can canonically define a translation operator. So you don't actually need to check it. But of course, given what we know about, given that this is supposed to match up with what we know about 2D CFT, you want that translation operator to be L-1. And then you need to check.
Right. Okay, thanks.
And that leads into the next statement, for which I'm going to use this sort of stronger understanding of how the Virus algebra is supposed to work. So finally, and this is to me sort of an annoying idiosyncrasy of language, but what we've been talking about so far are what are defined as vertex algebras, and a vertex operator algebra is a special case of a vertex algebra, which is Z-graded and which has a conformal vector named omega, which has the property that if you take the local field associated to that vector and do its mode expansion, then the endomorphisms appearing in that mode expansion will obey the Virus algebra with some value of the central charge. And you additionally need L-1 to be the translation endomorphism for your vertex algebra. And you want L0 to act as the grading that you started out with on your vertex algebra. So these are all what you would think of as the most reasonable conditions to impose. So this is saying that a vertex operator algebra is a vertex algebra that has a Virasoro vertex operator subalgebra that relates to translation and grading in the obvious way. And finally, because I'll mention this name later, a vertex operator algebra is said to be of CFT type if it's actually n-graded, so no negative conformal dimension pieces, has finite dimensional weight spaces, and the zero weight space is one-dimensional, which is just the vacuum. So this is of CFT type because it's rules that you would say that you should have if you were actually encountering this thing through a CFT. Okay. So reflecting on this example, in the Virasoro vertex algebra, everything is made from this operator T and its derivatives via normally ordered products. And so we only needed to check sort of one thing in order to verify the axioms. We can abstract from this a little bit. We say that an element of a vertex algebra is a strong generator if you cannot write it as the normally ordered product of any other two elements of your vector space. So in this Virasoro example, the conformal vector was the unique strong generator of, or the unique homogeneous strong generator of the vector space. And then a vertex algebra that only has a finite number of strong generators, so for which all but a finite number of states in your space can be written as normally ordered products of other things, is called strongly finitely generated. And so we were implicitly in this Virasoro example leveraging the fact that the Virasoro algebra is strongly finitely generated. The Virasoro vertex algebra is strongly finitely generated, sort of manifestly. And so we only needed to check some sort of locality condition on the strong generator.
But here I'm really destabilized, Chris. So for example, I realized that when we talk about an element A belonging to V, one way to see it is like to think about some basis elements and so on. But suppose that I take some infinite sum of basis elements with arbitrary coefficients. How am I supposed to think of such an element of my vector space? Is this an element of a vector space or not at this stage?
So we're in this Z-graded setting where things are, where our vector spaces are direct sums, so you don't get infinite elements.
So when you say element, every element, we really should say like every element of each of these finite grading pieces.
Well, no. So if you for infinite direct sums, the convention is that the elements of the direct sum only have finitely many terms in the expansion in terms of the.
Sure. Yeah. That's sounds good. Okay. Thank you. I'm spec stabilized.
This is so when this sort of issue of of how you think about sort of infinite elements that look like infinite sums is indeed an issue in various places in sort of the structure theory, and you need to sort of work with elements of the completion of these direct sums, which in principle are infinite sums, but not for what I'm saying right now.
Okay.
If you ever need to spend some time with the Frenkel-Benz V book, this is their V bar is the thing that includes infinite sums. Okay. Okay, so we have this notion of strong generators and of strongly finitely generated vertex algebras. And it's going to turn out that one can be sort of more aggressive about sort of trying to tell a story where you focus only on these strong generators. But before that, I need to report or recount an important result, which is a familiar looking derivation. You've probably seen it in Polchinski if you studied Polchinski or elsewhere. So from the OPE, and here I'm going to write down expressions that make sense by virtue of this analytic reinterpretation of locality, where things are actually operator-valued meromorphic functions. From the OPE, you can derive the commutation relations of the modes of any two of these vertex operators. And the cartoon is this one. You look at contour integrals where A and B first go around concentric circles where A is outside of B, and then go around concentric circles where A is inside of B. Oops. And the difference between these can be contour deformed to a situation where A is getting integrated in a contour around B, and then that sort of composite construction is getting integrated around the origin. And if you plug in arbitrary powers of Z and W when you do this, and use the analytic associativity condition that I had earlier in the form of the OPE, you get this commutation relation, which says that commutators are dictated by the singularities in the OPE in this definite way. So you only have the sum of n greater than or equal to 0 of this quantity. A greater than or equal to 0 mode acting on B is giving you a singular term in the AB OPE. But maybe a slightly better expression for this, instead of thinking of it in terms of commutators of modes, you can think of it as sort of an associativity condition for triple products. So sort of A OPE with B, OPE with C, and selecting out certain terms. So if I just take this expression and put in a C on the right-hand side, then I get what I've written as star here, but there's more of a mental adjustment, thinking of it instead of a commutator on some sort of Lie algebra of modes in endomorphism of V, we think of this as sort of a set of conditions on terms in OPs, even though they're secretly the same. Now, if you stare at this for a while, and I don't encourage you to do it right now because I'll go too fast, but if you were to stare at this for a while, you would realize that in the case where either M or K are negative, what this condition is telling you is how to take the OPE of A or B with some sort of normally ordered product of A with C or B with C, maybe with some derivatives sprinkled in. Or in the case where they're both negative, it gives you a rearrangement rule. So it tells you how to relate A, B, C with B, A, C, maybe with some derivatives sprinkled in again. On the other hand, when M and K are both non-negative, this condition reads as a consistency condition amongst the singular terms that appear in the OPE. In an honest vertex algebra or vertex operator algebra, this will necessarily hold, but it's a self-consistency condition amongst data that otherwise looks a little bit independent. And that can be turned around, that sort of way of reconfiguring the order of things can be turned around and used as a different set of axioms, which is much more useful if you're trying to construct strongly finitely generated vertex operator algebras. And the idea is to propose a set of strong generators. So I don't have a vector space and an OPE structure already. I'm building it up. So I'm going to propose a priori that I have a set of objects that are going to be called strong generators. And I'm going to prescribe their singular OPEs to tell me about some of the actions of sort of negative or positive modes of one acting on another. And then you use these identities that I had above, which are elsewhere called Borcherdt's identities, in order to, first of all, fix the OPEs between my generators and normally ordered products. So this was in the case where M or K was negative here. And then impose the condition for the case where M and K are positive, this consistency condition on singular OPEs, impose that on the case on the strong generators as an axiom, and then try to solve. So I have some ansatz for a finite number of singular OPEs between a set of strong generators, and I try to impose these consistency conditions. And if I can solve them, then I'm going to say that my vector space of the corresponding vertex algebra is the space of normally ordered products of derivatives of these strong generators that I instantiated at the beginning, modulo the reordering identities that follow from the Borcherdt's identities. So that's a nice idea. It's not completely obvious that it's going to be a self-consistent procedure. I wasn't very careful about this thing that I'm modding out by. Maybe there's some sort of inconsistencies I'm going to run into when I try to define the set of relations that I get with these reordering identities. So you have to do some work in order to show that this is a valid procedure. And it has been shown in a PhD thesis of Chris Thielemans, who also wrote the Mathematica package that everyone I know uses to do calculations with vertex algebras. And then that's sort of more of a physics PhD thesis than a math PhD thesis, so it's not quite phrased as rigorously as, you know, definition, proposition, lemma, theorem. That is done in a paper by Victor Katz and Alberto de Sol from later, where the relevant terminology that I won't define. I've abused you too much with definitions today, but the sort of thing that you define using this procedure is what's called the universal enveloping vertex algebra of a nonlinearly conformal algebra. So you try to define the sort of mathematical gadget that you are using when you say, I'm going to define strong generators and their singular OPEs only, subject to some consistency conditions. That data is a so-called nonlinearly conformal algebra. And then there's a automatic operation that turns it into a vertex algebra of the type that is sort of sketched out in these words. So that's the vertex algebra bootstrap procedure, if you will. Of course, physicists were doing this at least a decade before the procedure had been really introduced as a rigorous operation. So back in 1985, when Zamolodchikov defined the so-called W3 algebra, the first affine W algebra, this is essentially what he was doing. It wasn't phrased in quite these terms, but it was equivalent. And he defined some funny vertex algebra that if you've seen it before, you know what it looks like. And if not, it looks like this goofy thing. Where in particular, the notable thing, if you're not already a W algebra person, is that in the singular OPE of this field W with itself, you get things that are normally ordered products of T's. So that means that the mode algebra of the stress tensor and of W don't close to form a Lie algebra, because in the commutators of the W modes, you're going to get products of L modes. So you automatically live in some sort of bigger universal enveloping algebra. That's what makes everything feel a little bit difficult if you don't approach it in the right way. And I should remark that there's a variation on this vertex algebra bootstrap procedure where you allow for the consistency conditions to only be satisfied modulo some ideal that you want to quotient by what you would call null states in a more physical setting. And I'm embarrassed to say, because this is a procedure that I use, that I can't find a formal treatment of this procedure along the lines of what appears in the paper by Katz and de Sol. So if somebody is rigorously minded, it would be a nice problem to work out the analogous theorem to this one about universal enveloping vertex algebras of nonlinearly conformal algebras in the case where consistency conditions are obeyed modulo null states. This is alluded to, the modified procedure is alluded to in both of the references I mentioned before, the one by Thielemans and the one by Katz and de Sol. But the definition, proposition, lemma, theorem treatment hasn't appeared, I don't think.
You said at one point that without the axiom for a translation operator, you can still define one using the other axioms.
Yeah.
But then in this construction of the bootstrappable VOA, you had this piece in brackets where you need derivatives and normal ordered products of strong generators. Are those related somehow?
I don't think I have something smart to say. So, I mean, in this sort of bootstrap approach, you're really taking a different approach. You're not. well, maybe I shouldn't say anything. I don't have something smart to say. So in this Bootstrap approach, you construct a thing that involves derivatives. In the original axiomatic approach, you can define the vertex algebra without a thing called T, and then you are going to get a canonical. I mean, it's not a fancy thing. I should just say, you know, if you have y of a z is some a n z minus n minus 1. This is the thing that you have in general. So here's a field. I'm going to claim that it's local. Then I want to define T on my vector space. I'm just going to do it. So remember that y of a z acting on the vacuum limit where z goes to 0 is just going to give me a minus 1 acting on 0. Then the translation is supposed to obey the property that the vertex algebra, the vertex operator associated to TA is supposed to be dz of this stuff. So that's going to be some nz a n minus 1 z to the minus n minus 2. So even if I haven't defined T, I can just write this thing. And then I can take z to 0, and I'm going to get a minus 2, 0. So as soon as I've given you the vertex operator, which tells me not only what a minus 1 is, but what a minus 2 is, now I get, so this thing is going to be equal to T of a. So that's the little and then, okay, you can check that using that to define the action of T on every element of your vector space gives you a T that satisfies the axioms. So that's how you can avoid involving T in the axiomatic definition. But I don't see a relationship between that observation and any feature of the more bootstrappy construction.
Yeah, it's just that when you said a strong generator was anything that cannot be written as a normal ordered product, I wouldn't normally say that a derivative of a strong generator is also a strong generator.
Okay, that's my mistake. It should be phrased more carefully. A strong generator is something which is not the normal ordered product of any other things, and it's not the derivative of something.
Oh, okay.
Yeah.
Yeah, it was probably just a brevity.
If we were using some sort of SL2 language, you would say that it should be a primary or a quasi-primary.
So I also have a question, kind of elementary one. I realized I don't understand one basic thing. Can you explain to me, in this VOA setting, if you have 3 fields of dimensions h1, h2, and h3, suppose I fix h1, h2, then can h3 be arbitrary, or is there some relation in h3 which is not?
You're saying to have a 3-point function?
Yeah. For example, if I know something about h1 and h2, can there be infinitely many allowed values for h3 or finite number of allowed h3s? A priori, it seems like I can have arbitrary h3. The reason I'm asking is that I'm wondering. So you presented this graded v is graded, but how many actually primaries are we going to have? Is it true that these VOAs always have to have finitely many primaries? Otherwise, we are going to run into difficulties with defining these operators as elements acting on your tensor product, because you only define tensor product as a sum, as involving finite combinations.
You're talking about finitely many Virasoro primaries?
Yeah.
No, I don't think there's any requirement that you have a finite number of Virasoro primaries.
But then we're going to run into a difficulty because we do OPE of two operators, and the OPE, so the OPE is supposed to be an endomorphism, but then endomorphism has to act from V to V. So it's going to give us something which is a sum of infinitely many Virasoro primaries, but you only defined V as a tensor as a.
Sure, I don't think you're going to have. I mean, I think in this sort of strongly finitely generated case I'm talking about. So remember, the endomorphisms are supposed to be order by order in Z in the Z. And so at a given order in the Z expansion, you're getting something which maps from a given Z graded component of your state space to another given Z graded component of your state space.
Okay, maybe this is going to save the day.
Yeah, this is if I have an infinite number of Virasoro primaries, but they're of increasing conformal dimension, which is what's going to be happening, then in a given weight space, I have nothing to worry about.
Okay.
Is that okay?
Yeah, thanks.
I mean, this is what happens, of course, in the honest conformal field theory case. If you have something, even if you have something which is like a, I mean, I haven't introduced the VOA definition of rationality yet, but if you have some rational conformal field theory whose chiral symmetry algebra is something bigger than Virasoro, then with respect to Virasoro, you're going to have infinitely many primaries. But then, of course, you organize things in terms of the bigger algebra to get sort of the usual rules of RCFT.
Okay.
Okay. I'm already 10 minutes over. I need to decide what to do.
You just continue.
Can I have 5 minutes?
Sure. To have as much time as you need.
Well, you don't know how many more pages I have.
5 more.
Okay, so I wanted to, don't worry, I won't really abuse people. I wanted to say something about what one encounters if you try to go learn about what are nice types of vertex operator algebras. And basically there are two types of conditions, roughly speaking, that you run into, and there are what I would call representation theoretic ones and algebraic ones, external or internal. So representation theoretic characterizations are properties that hold at the level of the family or the category of modules for the vertex algebra, which I'll define momentarily. Whereas if you're sort of more focused on the intrinsic algebraic structure of the vertex algebra, you might be more interested in something you could just check in some automatic way using the data of the OPEs without having to conjure some sort of thing that it acts on. Okay, but the representation theoretic ones are the sort of characteristics that dominate the literature. So let me try to semi-quickly define this. It's going to be a lot of definitions now, but this is just to hopefully give people a flavor. So if you have a vertex algebra, you can define what's called a weak V module for your vertex algebra, which is a state operator map which maps from your vertex algebra to operators that are fields on your module. So this is the picture you would expect, again, from sort of cartoons in physics. You have some module sitting here. That means that you have elements of your vertex algebra. They can come hit it, but it stays the module. So that means that given an element of V, you get a collection of endomorphisms of M, not of V. And this should obey some sort of consistency conditions, which here I've written in the sort of non-analytic way. And I'll just go through them quickly. It's the statement that if you act with two different elements of your vertex algebra on the same module, then if you do it in two different orders, you should have this same locality condition, that there are different expansions of the same element of this sort of space of rational thing. So this is analogous to this sort of analytic continuation of operator valued meromorphic functions. You have a slightly different condition that's giving you associativity, because in the associativity case, you're going to bring A and B together in sort of the vertex algebra way, and then they're going to act on the module in the module way. So here you have a expression that involves one ym and one y instead of two yms. But nevertheless, that should give you the same expression. Meaning that when you expand this thing as an element of an appropriate space of formal series, that thing should be an expansion of the same underlying element of the more rational space. So a weak module is just something where the vertex operators act self-consistently. An admissible module is one where your module space is graded and where the vertex operators act in a grade consistent way. So we had this rule that if you had a homogeneous vertex operator, it acted between sort of different graded components in an appropriate sense. And here you're going to demand the same thing at the level of acting on this other vector space, this module. And then a weak V module is ordinary in the case of a vertex operator algebra if it's graded and the grading is a conformal grading with respect to the conformal to the Virasoro subalgebra. So L0 should act on the graded components by their grade. The graded components should be finite dimensional, and for a given graded component, you shouldn't be able to lower the grading arbitrarily, so you should have energies bounded from below. So an ordinary module is the sort of thing that you would actually be looking at if you ever ran into an object in an honest CFT that was supposed to be acted upon by a vertex algebra. And in order of strictness, ordinary is the strictest, and then admissible, and then weak. And it's in terms of these sorts of different levels of niceness of modules that vertex algebras are characterized as being rational or regular or strongly rational. And these are some definitions which make enough sense, but they look impossible to check. And in fact, the literature on them is, you have to put in a lot of work to checking that these sorts of things are true. So a vertex algebra is called rational if an admissible module definitely decomposes into a direct sum of simple admissible modules. Simple meaning that it doesn't have any proper submodules. So nothing, no subspace that sort of transforms into itself when you hit it with the vertex algebra. So in that case, you restrict by hand to these reasonably nice admissible modules, and you say that they need to be completely reducible. So that needs to be a sort of nice representation category. A vertex algebra is called regular if every weak V module. So in this case, you allow sort of the most general type of module, but nevertheless, if every weak V module actually is a direct sum of ordinary modules. So that's what we would like. If you want to be able to work representation theoretically and say stuff about what's happening in a more physical setting, you would hope that you could sort of work with the full family of modules, because that's something that sort of should close on itself under various operations for combining representations. But you would hope that what you're talking about when you work with all of the modules is secretly only reasonable looking things.
Chris, can I ask a naive question? Why can't we just take M equal V? Why do we need this separate module? Why can't we just, why do we need to introduce a new vector space and not just act in? Yeah, I'm confused.
You don't have to if you don't care about the representation theory of these things. So V itself is a module over itself.
Yeah.
But you could have other modules over V. So in an RCFT setting, all of the non-holomorphic fields in your theory organize as representations of the chiral symmetry algebra.
I see. Okay, so you want like to you would like to consider correlation functions where the outside fields are not necessarily holomorphic, but the inside stuff is holomorphic. This is the kind of things that you have to keep in mind.
That's the type of thing, although I'm not even talking about correlation functions yet. Right now,
Yeah,
I'm
but eventually, yeah.
sort of consistency with the symmetry algebra itself.
Okay.
Okay, and then with all of these definitions, if you have a regular vertex algebra, vertex operator algebra, which is of CFT type, which remember means that the conformal grading is bounded at 0 and only the identity operator has grade 0, then that's called a strongly rational vertex operator algebra. And the point of introducing this is that it's these strongly rational vertex operator algebras that obey the rules of rational conformal field theory, if you've learned this from sort of more of the Moore-Seiberg type of physics approach. The chiral algebras of rational conformal field theories are, you might have thought they were rational. They are rational, but in fact they're regular, and they're actually strongly rational. So if you've spent some time with RCFTs, all of your favorite chiral algebras, Virus algebra at the minimal model values of the central charge, WZW models that have affine Kac-Moody current algebras at positive integer levels, lattice vertex algebras with positive definite even lattices, even some minimal series W algebras. These all have this regularity property. In some cases, this has not been proved so long ago. So Arakawa proved the regularity of sort of the most popular family of W algebras 9 years ago. And it's for these types of vertex algebras that the general RCFT wisdom that you will have learned from Moore and Seiberg's papers from a long time ago actually rigorously applies. And again, this is actually recent developments in mathematics, relatively recent. So going back to 2008. So if you have sorry, I wrote regular here, this should be strongly rational. If you have a strongly rational vertex operator algebra, then you get the Verlinde formula, which has to do with so-called fusion rules, which I haven't reviewed. You get that the characters of your modules transform as a vector valued modular function. You get that the category of modules is actually a modular tensor category, which is a great sort of thing. So I'm not going to attempt to tell a story about this now, except to say that these are the sorts of properties that one sort of either intuits or believes should be out there in reasonably nice cases based on RCFT. And they're only proven to hold if you have this sort of strong condition at the level of the category of modules of the vertex algebra. So those are important and good results, but they also, if you're sort of a lowbrow person, they're a little bit intimidating, because how do you get a handle on sort of the full set of weak modules of some vertex operator algebra in order to prove something like regularity? Well, very smart mathematicians can do it, but it's very abstract. Which leads me to my final topic, which is something that starts to get close.
Sorry, can I ask if the RCFTs you refer to, are they unitary?
Not necessarily.
All right.
So for example, for the Virasoro minimal models, I meant the full set of minimal models.
Okay, thanks.
Yeah, of course, there's a whole. I'm intentionally ignoring the whole structure of unitarity, which of course is an extra sort of structure that you can put on vertex algebras and their modules.
Yes, thanks.
Okay, so you might hope that there's going to be some sort of intrinsic condition at the level of the vertex algebra, which would actually serve the purpose of establishing these sorts of rationality, regularity results, so that you didn't need to do something sort of in the category of V modules in order to know these nice properties. And there's something which in a way gets close. It doesn't turn out to be equivalent, but it still sort of has led to a lot of work in the subject, which is something called C2 cofiniteness. And this is something that you can actually get some intuition for. So you define a vector subspace of your vertex algebra, which is everything of this form, A and B and V, A minus 2B. And if the translation isn't automatic in your head, this is looking at things which are normal ordered products where one of the operators is a derivative of something. And it requires a little exercise, but you can show that actually if you take an arbitrary normally ordered product of a bunch of fields with nesting of parentheses however you like, and if there's a derivative acting anywhere, then that thing lives in this space. So you need to use various reordering rules and things to show it, but it's true. So morally speaking, and in fact, technically speaking, this is the subspace of all of the states whose corresponding operators involve any derivatives. And using the Borchardt identities to tell you about various reorderings, you can show that if you take the normally ordered product of two states or of two operators, and you change A for B, even though normally ordered product doesn't commute, it is the case that the difference, the commutator, lives in this C2 space. And similarly, if you try to reorder in sort of an associativity way, and you look at the difference between the two different orderings, so this would be called the associator between A, B, and C, then that thing lives in C2 of V. And that means that if you just take a big vector space quotient and work with your vertex algebra state space modulo this C2 subspace, then the operation of normal ordering gives you some sort of a commutative associative product. And that thing is called Joux's commutative algebra. This thing was first defined by Joux in 1995, I think. So this is some footprint of a vertex algebra in a much simpler world. And if you have a strongly finitely generated vertex algebra, then this is going to be a finitely generated commutative associative algebra. And you can check more things. So if you look at the zero subscript operation, so this, if you recall the conventions, corresponds to looking at the simple pole in the OPE between two vertex operators, then the symmetrizer of that lives in C2 of V. And this combination, which you might call the Jacobiator, this is the thing that should be zero if a bilinear operation satisfies the Jacobi identity. That thing lives in C2. And this quantity, which you might call the Leibniziator, which checks whether the Leibniz identity is satisfied between this OPE, this simple pole operation and the normally ordered product, that thing is in C2 of V. And that means that the simple pole operation modulo C2 of V defines a Lie bracket which satisfies the Leibniz identity, so the whole Joux commutative algebra gets the structure of a Poisson algebra. So there's a canonical Poisson algebra associated to every vertex algebra. And in a strongly finitely generated vertex algebra, this will be a finitely generated Poisson algebra. And in terms of that thing, then I gave examples. Right, so these things are not hard to compute if you have a vertex algebra which is presented in terms of strong generators and singular OPEs, because you can sort of just write things out and look for derivatives and drop them. And so in the Virasoro vertex algebra, this sorry, did I call it RV? Yeah. This big quotient space that you get just looks like polynomials in a single generator, which corresponds to your strong generator. And the Poisson bracket is 0 because the simple pole between T and T in the Virasoro algebra is T prime, but that's a derivative. And then if you go to one of the minimal model values of the central charge, this introduces null states for the Virasoro algebra. So you're going to get something which looks like this. This is the general form of the first null state that you encounter in the P comma Q Virasoro minimal model. It's T to the power P minus 1 Q minus 1 over 2, which is always an integer, plus something involving derivatives is equal to 0. So in the C2 subspace, this means that T to the power P minus 1 Q minus 1 over 2 is set equal to 0 when you're working in the quotient by null states. And so in that case, the Zhu commutative algebra is a finite dimensional vector space generated by T, but where T to some particular power is 0, so T is nilpotent, again with a trivial Poisson bracket. Some other examples, if you look at symplectic bosons, so a beta gamma system, then you get a Zhu commutative algebra, which is just a polynomial algebra on two variables x and y, whose Poisson bracket is non-trivial. So this looks like the phase space of classical mechanics on the real line. X is x and y is p. Let's not belabor the extra points. These things are not so hard to compute if things are presented as strongly finitely generated things in terms of OPEs. So finally, to conclude, this seems to be a good condition on vertex algebras, is that this C2 algebra be finite dimensional as a vector space. So we saw in the previous very fast
I wonder if it's my problem. No, connect.
We're not muted, but
No.
well,
I think we all have the problem.
yeah. And now we lost it.
It's not the end. Let's just wait for Chris to come back. Notices if he's not. I sent him a message. He's on Slack actually. And
He should have been kicked out of Zoom, so it would be surprising
if he didn't notice.
I hope you realize he noticed. Yeah, you realize the connection.
I can go knock on his door and ask.
Yeah,
He's
yeah,
coming.
Connor, that would be.
He's back.
He's back.
Hi, sorry, my computer stopped going. So I mean, maybe that was the universe telling me that I had really gone on for too long, but let me try to finish up very quickly if I can get this to reshare my screen.
They asked me to check if you know you're disconnected.
I'm back connected. Thank you. Sorry about that, everyone. Don't know what happened. Okay. So apologies. I think I was in the middle of saying that, well, based on the one example that I flashed before about the difference between the Virus algebra in the case when you were at generic level, where this Jou commutative algebra was an infinite algebra, infinite dimensional as a vector space, and the case corresponding to minimal models, where it was finite dimensional as a vector space, you could very conjecturally suspect that there's something good about this being a finite dimensional vector space, and it's the case. So such a thing is called a C2 cofinite vertex operator algebra. And there are some results. So in particular, if you have these strongly rational vertex algebras, which were the ones which are sort of one's favorite to work with because they basically behave like RCFT chiral algebras, those things are always C2 cofinite. This is a result from 1998 of Haisheng Li. And in fact, if you have vertex algebras of CFT type, then regularity, this sort of strongest finiteness condition at the level of modules, is equivalent to rationality along with C2 cofiniteness, which is a result from 2002. But before one gets too excited, it's known that C2 cofinite vertex operator algebras are not necessarily rational. So it's not as strong. You're not so lucky that this is a purely internal condition, which implies sort of the best case that you would like. So symplectic fermions, which are the sort of things actually that in my previous lecture we were running into as the vertex algebra associated to free vector multiplets in 4 dimensions. Those things are known to be C2 cofinite, but irrational. So this is some sort of middle ground. There's a nice result due to Jou and supplemented by Miyamoto, which says that if you have this C2 cofiniteness property, which in principle is not so hard to check, that it implies something like the modularity of characters, which is an important property in RCFT. This is the story of how you build modular invariant partition functions in RCFT. In the C2 cofiniteness case, you find out that the characters of your simple ordinary modules, those are sort of the good modules that are the ones that you would naively pay attention to in a physical setting. If you look at their characters, so the graded trace where the grading is carried by Q, then those things have some modular properties. So they transform as components of a so-called logarithmic vector valued modular function under the modular group action on tau, where there's Q to e to the 2 pi I tau. In the case where this is not logarithmic, then you're dealing with sort of the RCFT type of transformation property. This is not quite as good, but it's still better than generic. generic vertex algebra characters don't have any reasonable behavior under tau goes to a tau plus b over c tau plus d. So this gives you the sense that this C2 cofiniteness property is sort of getting you into the vicinity of really nice vertex algebras, but it's not quite as strong. So that's where I was planning to cut off, and this has now been a lot of information, some detailed, some sketchy, about sort of the landscape of vertex operator algebras from more of a mathematical formal point of view. Next week, I'm going to come back and try to say a little bit more about the vertex operator algebras that result from this four-dimensional SCFT construction, what their properties are, what some examples are, and then we'll be able to sort of compare them to the framework I've set up today of sort of what counts as a good vertex algebra, what counts as an interesting vertex algebra. There's some new property, which is not quite C2 cofiniteness, that we'll meet, called quasi-leastness. And we'll see if I get through everything. But that's going to be the plan. Sorry for going way over the ostensible time.
Thanks, Chris, but we interrupted you a lot. Let's thank Chris for his second lecture. Are there any questions?
Yeah, perhaps I can ask a question about
Sure.
the modules. I'm still a bit confused. So I thought, did I see a YM of Z? So do modules generate holomorphic or meromorphic fields? Because I'm thinking like in relation to the answer you gave to Slava, I don't know if I have sigma, like operators that only exist as non-meromorphic operators, I wouldn't know how to generate a field out of those. So what is this YM of Z?
Right. So okay. Thank you for that question. I should have accentuated this point when I made it. So these YMs, these are not maps from M to fields. They're maps from V to fields. So
right.
This is the thing that you define if you want to understand how an element of your vertex operator algebra, the actual meromorphic algebra, how that acts on this other vector space. So we're not in this piece of the story, we're not seeing anything like the sort of non-meromorphic OPE between modules. We're not seeing fusion, which is the buzzword, of course, when you start talking about trying to sort of compose different modules. This is just sort of the zeroth thing where you say, if I have some operator which is not part of the meromorphic sector, I should be able to hit it with meromorphic stuff and have it sort of transform in some appropriate way. And then there's some consistency conditions.
Okay, thanks.
Okay, well, if there are no other questions, then I guess we should thank Chris again and pause for 15 minutes. Thanks, Chris.
Thank you.